Okay, hi everybody. So we're going to be in probability for this whole week. And what I want you to know is that this takes practice. So not memorization, just practice using your intuition more than anything else. Typically, what you're thinking first is usually correct. There are many rules. There are many ways to solve the probability problems. But if you use your intuition and go with that, that's usually the most successful. So I'm going to try to demonstrate that as we go. The two documents that I have up are what we're going to cover today and Thursday. So we will not get through all of these. So just know that we're just going to work on these two documents for the next couple Zoom meetings. So let me share my screen. And the first ones I'm going to do are off of I think I might have called it probability activities. Let me just pull it up so you can see which one it is. Oops, wrong class. I need to share here we go. Share. Okay, I need this one. So yeah, this is the first one I'm going to start with. So the probability practice problems, let's start here. I'm going to do the first few on this worksheet, and then we're going to switch to the other worksheet. Okay, so, and also know that you have only learned, as far as what the calendar is showing, 5.1 and 5.2. So there is so much more to learn in 5.3 and 5.4. 5.6 is actually a summary of all of the probability methods. So that'll be nice to have that wrap up towards the end. But just know you don't know everything yet. So I'm exposing you to just different probability ideas. And we're just going to practice them, and you will get better at it as you move through your homework this week. So let's start here. And this first one, we're going to try to round all the answers to 4 decimal places if needed. And we're going to show the fractions so that we can identify how to get the probability answer. So just giving the decimal answer, that is also something to know if you want help from me. It's really important to write the fraction part out so I see where you're getting your decimals, because it could be so small, such a small discrepancy in the decimal that it might be that how you're calculating the fraction is where the issue is. Okay, so let's do number 1. The following table represents the results of a survey in which 400 college students were asked whether they listened to music while studying. Okay, this table is a 2x2 because there are 2 variables, male, female, so gender, and then listen, not listen, do not listen. That's the other category. So it's a 2x2. It's also sometimes called the contingency table. I'll write that out. So it's just a way that data is summarized and given to us. So as we're looking at this, we want to interpret it. What I always like to do when I see a table like this is I automatically put an extra row and an extra column that are going to tally the total. Whoops, again. So I want the row total and the column total. So the row totals is here. Trying to draw my lines so they make sense here. Okay, so I'm just adding a couple other boxes. So if I take row total, so that means I'm going to look at males. So males is 121 plus 78. So 121 plus 78 is 199. And then when I look across the row for females, 147 plus 54, that's 201. So I know there's 201 females in the study and 199 males. And the total, when I add them, is 400. Because 199 plus 201 is 400. And that makes sense because it says there's 400 college students. Okay, so now let's look at the column totals. So the number of students that listen is 121 plus 147 is 268. I'll do the same thing for the number that do not listen, 132. So when I add across that row, 268 plus 132, I get 400. So these just help me with answering the question. So I just take that moment to calculate those totals. All right, now let's look at part A. Part A says, find the probability that a randomly selected student does not listen to music while studying. Okay, so we're looking out of the total number of students, so out of 400, how many do not listen to music? Okay, so I can see from my total that there's 132 that do not listen to music while studying. So I know that I'm going to have 132 divided by 400, and we can reduce that. So if we divide by 4, 4 into 400 is 100. 4 into 132 is 33. So that's a simplified fraction, or we can write it as a decimal. Typically, probability is given with decimals. So we usually interpret them off of the decimal. And 0.33 is exactly 33 hundredths. Okay, let's move on to part B. Part B says, find the probability that a randomly selected student listens to music or is male. So we want a student who listens to music or is male. So because you can have a male student that listens to music, these are not disjoint. They're not disjoint because you can have because the categories overlap. So let's think about how we could calculate this. So out of the 400 students, the number of students that listen to music, I'm going to delete some of these highlights. Okay, the number of students out of the 400, the number of students that listen to music out of, oh, wrong pen. Whoops. This is what I want. Listen to music, there's 268. So 268 out of the 400. Plus the number of students that are male, the number of students that are male are 199. So do you see that I just counted, I counted the students that are male and listen to music twice. So because I did that, I want to subtract off where I overlapped and counted those students twice. So I'm going to subtract off 121 out of 400. So that's what happens when you're trying to find probabilities where the events are not disjoint, is you have to subtract off where they overlap. So then we end up with, out of the 400 in the denominator, we get 346 by taking 268 plus 199 minus 121. And if I simplify this by dividing by 2 into the numerator and the denominator, I get 173 out of 200. And that divides out to exactly 0.865. So when you learn this, this is called the addition rule. Okay, the addition rule, let me get some more paper here. The probability of A or B is the same as probability of A plus the probability of B minus the probability of A intersect B. I use the word or, which is also the same as union. So or is the same as union. Intersect means and. So the probability rule, the addition rule, and this is where I'm telling you that you don't really need to memorize this. This is more about thinking about what makes sense. So as we look at, I just erased all that. As we looked at the work we had just done, and I'll have to rewrite it because it got erased from my page, but we had 268 divided by 400 plus 199 divided by 400 minus the overlap. So probability of the student listen to music, and then the probability of the student being male, and then you have to subtract off where they intersect, where they overlapped. Could we just look at our table? And in our table, erase all these marks now. In our table, could we just look at where the students listen to music or is male? So listens to music is here, listens to music is here, and male is here. So we could add all those up and we would get the same result. We chose this method, which was the addition rule. Okay, so I spent a long time on that. Let's move on to the next problem. Problem number 2. In a group of 100 teenagers, 61 received their driver's license on the first attempt on the driver's certification exam, and 18 received their driver's license on their second attempt. What is the probability that a randomly selected teenager received their driver's license on the first or second attempt? So what we are looking at is out of the 100 students, the probability that a student received their license on the first attempt, it says 61 received on the first attempt. Plus, out of the 100 students, 18 received their license on their second attempt. So do you see now that these are disjoint events, different than the first problem, because a student cannot receive their driver's license on their first attempt and their second attempt. If they received their license on their first attempt, they wouldn't have a second attempt. So those are not disjoint, and we can just add them without subtracting anything. And we get 61 plus 18 is 79, and that simplifies as a decimal to 0.79. Okay, moving on to number 3. Number 3 says, River Road neighborhood has 100 households. 48 households have a dog as a pet. Of these, 32 also have a cat. Given that the household has a dog, what is the probability that it also has a cat? Given that the household has a dog. So that's not out of the 100, it's out of the 48. So out of the 48 that have a dog, 32 also have a cat. 32 out of 48, if I simplify that by dividing 16 into both, I get 2/3. And here's where I'm going to round, so I'm going to do approximate. And I think I said 4 decimal places. I said round to, yeah, 4 decimal places. So 0.6667 approximate. So there's nothing to add together, but we had to designate, given that the household has a dog, given that out of the 48, 32 also had a cat. Okay, now we're going to spend some time in this next problem with marbles. Okay, a jar contains 4 red marbles, 3 blue marbles, and 5 green marbles. I will randomly draw 2 marbles from the jar without replacement. So important to know how many and whether you're going to replace the marble or not. One way to help you organize the information and how to create a visual of the sample space of what it would look like if you drew 2 marbles is to draw a tree diagram. In a tree diagram, we start with the options on the first draw. So when I draw, I'm either going to draw a red marble or a blue marble or a green marble. So my tree, my first draw is either going to be a red, blue, or green marble. If I draw a red marble first, then from there, I'm still going to have 3 options on my second draw. My second marble is going to be a red, blue, or green. So right now, my sample space is red on the first, red on the second, red on the first, blue on the second, red on the first, green on the second. If I draw a blue marble first, I'm still going to have those 3 options: red, blue, or green. So my sample space is going to also include blue on the first, red on the second, blue on the first, blue on the second, blue on the first, green on the second. And then my third layer means that if I draw green first, I can have those same options for the second draw: green and red, green and blue, green and green. These are all of the ways I can draw 2 marbles out of my bag. This is the sample space, all the options of drawing 2 marbles. Notice that red, blue is different than blue, red. So even though it's RB and BR, red is first, blue is second. In the other one, blue is first, red is second. So those are different. So there's the sample space. And that's what it asked me to do for part A. A tree diagram does not work for if I was going to draw, if I wanted to draw 5 marbles. Do you see that I would have 5 layers? So my first layer is this red, blue, green. My second layer, my second draw would be here. And then off of each of those ends, I'd have 3 choices. So that would be my third marble, then my fourth marble. So it would just be so expansive, you would need the whole side of your house to draw the tree diagram on. So not very effective for larger numbers, for drawing more than 2 or 3 things, but it works very well for something like this. All right, so now let's go to part B. Find the probability for each outcome. These are not equally likely because I have 4 marbles, 3 marbles, 4 red marbles, 3 blue marbles, 5 green marbles. So I have a higher probability of drawing a green marble than I would a blue marble because there's 5 greens and only 3 blues. So these are not equally likely. So for each draw, the probability of drawing a red, how many marbles are there total? There's 4 plus 3 is 7 plus 5 is 12. So 4 marbles, 4 red, 3 blue, 5 green. So 12, out of the 12, there's 4 red marbles. So the probability of drawing 1 red marble is 4/12. I'm just going to leave it in that form right now, just so that the concept is there. I know I can reduce it to 1/3, but I'm going to leave it like that. Probability of drawing a blue marble then, well, there's only 3 blue out of the 12. And the probability of drawing a green marble, there's 5 out of the 12. So that's why they're not equally likely. So I'm trying to find out the probability for each of these sample space options, events. So the probability of drawing red, red. I know that I have 12 marbles and there are 4 red marbles. So that's drawing my first red marble. Because it is without replacement. It is without replacement. That means I'm going to put the first marble to the side. So now I only have 11 in my bag to draw from. I put a red marble to the side because my first marble was red. So now I only have 3. So then I would multiply those out and I would get 12 out of 132. And you could get your decimal from there. I just want you to get the concept of how we're coming up with these fractions. So you can take 12 divided by 132 and get approximately 0.0909. Okay, let's do the same for the next one. The probability of red, blue, out of 12, there are 4 red marbles. Put 1 marble to the side, so now there's only 11. How many blue marbles are in your bag? There's still 3, so there's 3. We get the same probability. Probability of red, green. 4 out of 12 for the red. There's only 11 in the bag. There are 5 green marbles. So 5 out of 11. So 20 out of 132. Let's continue in the same pattern. So out of the 12 marbles, I'm trying to find the probability of drawing a blue marble, then a red marble. So a blue marble, there are 5, how many blue marbles? 3 blue marbles, so 3. 11 left in the bag, and there's still 4 marbles to choose from. Probability of blue, blue. Out of 12, there's 3 blue out of the 12. Now there's only 11 in my bag. And because I took a blue marble out on my first, I only have 2 blue marbles left in the bag. So 6 out of 132. Probability of blue, green. 3 out of 12. For blue, 11 in the bag, and in the green marbles, we have 5. So 15 out of 132. And the last 3 here. So now we're looking at green marble first. So out of the 12, there's 5 green marbles. So 5 out of 12 is the first fraction. And drawing the red marble, we have 11 in the bag, and there are 4 red marbles. Probability of green, blue. 5 out of 12 for green. 11 in the bag once you take the green out, but there are still 3 blue marbles. Can we do the right one? Yes, there's still 3 blue marbles in the bag. So 15 out of 132. And then the last probability, green, green, is 5 out of 12. Take green marble out, there's 11 in the bag, And because you took a green marble out, there's only 4 green marbles left. Okay, I'm going to skip part C. Well, I'm not. I'm not going to skip part C. Let's go ahead and go into part C. Part C is, what is the probability that the second marble is red, given that the first was blue? Probability that the second marble is red, given that the first was blue. Okay, so we are not going to use what we just found for probability. We're going to think about what this means. What is the probability that the second marble is red, given that the first was blue? So if we know the first marble is blue, there's no probability of taking that first blue out. There's no probability of drawing a blue. The first marble is blue, period. The first marble is blue. So if the first marble is blue, then there's only 11 marbles in the bag. And I'm just thinking that the marbles are in a bag that I'm taking them out of. So now there's only 11 marbles left in the bag. So out of those 11 marbles, what is the probability that you get a red marble? There's 4 red marbles. So it would be 4 out of 11. I'm going to shift and take you into the next worksheet. So we will work on the other problems on the next meeting. So let's go ahead and go into the other worksheet, which has the deck of cards on the front. Okay. So as we study the cards, some people are not familiar with cards. I grew up playing cards with my family and my grandparents. So these are all really good memories for me. Cards are often used with gambling as well. So a lot of people make money because of the probabilities involved with card playing. And a lot of people lose money because of the probability that you're going to win. Across the top, notice that these are all, okay, notice that half of the cards are red, half the cards are black. So we recognize that. Then there's 4 different suits. The first suit across the top, you have clubs. And then you have spades is the next row. And then you have hearts. And you have diamonds. So these are the 4 different suits. Then we also know they all have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you have jack, queen, king. These are called the face cards. Okay, so a miniature lesson on the basics of what the cards are. There's 52 cards in the deck. So let's go to part 1. So part 1, and notice on that worksheet, I didn't photocopy the questions because they're just easy to write down. So on part 1, it says randomly draw 1 card from the deck. So part 1, we are randomly drawing 1 card. So if we randomly draw 1 card, then it's out of the 52 cards. So part A says, find the probability of drawing a 5. So out of the 52 cards, how many are 5s? And we can see right here that we have 4 that are 5s. So the probability of drawing a 5 is 4 out of 52, which reduces to 1/13. And I'll take this out. We'll go out to 3 decimal places on this one. I don't know if I told you. I didn't tell you where to round on this worksheet, but let's just right now say we're going to round to 3 decimal places. Okay, what I want to see when you show any of your work is that first fraction, because I want to make sure that you are performing this probability correctly to get to the answer. Okay, part B says, what is the probability of drawing a face card or a heart? Face card or a heart. Okay, so are these disjoint? Can you have a face card that is a heart? Yes, you can, right? You can have a face card that is a heart, so these are not disjoint. So the probability of drawing a face card out of the 52 So face cards, if I look in the corner, there's 12 face cards. It's my 12 face cards. And so I know that I'm going to have 12 out of 52 for the probability of a face card or hearts. So if I look at how many hearts, there are 13 hearts. So 13 out of 52 is a probability of drawing a heart. But I just counted hearts that were also face cards. So I just counted the Jack, Queen, King twice. So I need to subtract off those 3 where they overlap, where they intersect. So this would be the probability of face card plus the probability of heart minus the probability face cards that are hearts. Okay, so if we calculate this, 52 is the same denominator, add across the numerator, 12 plus 13 minus 3 is 22, and that is approximately point, oops, not that, 0.423. Okay, moving on to part C. Find the probability of drawing a black card, ace, or face card. Probability of drawing a black card, ace, or face card. Black card, ace, or face card. Okay, so instead of using any rules, I'm just going to look. Probability of drawing a black card. Okay, well, there's half of them. Okay, black card, ace. There's 2 more here. So right now I have 26 plus 2 more. So now I have 28. And then the face cards, there's 6 more face cards. So I have 34 altogether. (34 out of 52), which is approximately 0.654. So it is okay to do that. I'm trying to illustrate some of the rules that you're seeing as you're learning this, because you may not always be able to look at the diagram and just count them. So you have to have some algorithms to help you get there, like I showed you in part B, but it's okay to count them as well. Okay, let's move on to part 2 now. Part 2 is we're going to randomly draw 2 cards. Oh, yikes. Okay, part 2. We're going to randomly draw 2 cards, and this is with replacement. So we're going to draw a card, and then we're going to put it back in the pile after we draw it. So that is what's happening for part 2. Okay, part A says find the probability of drawing a 2 and a queen. Okay, remember I have mentioned that union is or, intersection is and. That's what we were using up here for like part B. Face card or a heart. So we added those options. And we had to subtract off because they were not disjoint. But we added them because we were drawing one card. We were just drawing one card and we were saying, what's the probability that that one card is a face card or a heart? So we added those options for that one. This, we are drawing two cards. So we're drawing one and another one. So this one's going to result as a multiplication, not addition. So I want the probability of a 2 times the probability of getting a queen. So the probability of getting a 2 out of the 52 cards, here's the deck again. Out of the 52 cards, we see that there are 4 2s. So the probability of getting a 2 is 4 out of 52. And the next one being a queen. And do you see that because I am replacing the card, my denominator did not change. So when we were drawing the marbles, that was without replacement, where I took the marble out and I put it to the side. So there was only 11 left in the bag instead of 12. This one I'm replacing, so the denominator stays the same. And then the number of queens there are 4 queens. So I come up here and I look and I see there's 4 queens. So the probability of drawing a 2 and a queen with 2 cards is, if you multiply 4 times 4, we get 16. If you multiply 52 times 52, you get 2,704, which is approximately 0.006. Okay, part B. Okay, let's see, part B. Find the probability of drawing a spade and a red card less than 5, not considering aces. So probability of drawing a spade and a red card that's less than 5. So I know this is with replacement and I'm drawing twice. So 52 is my denominators. I'm multiplying because I'm drawing 2 cards. The probability of drawing a spade, there are 13 cards that are spades. How many cards are less than 5 that are red that are less than 5, but not including aces? So red less than 5, but not including aces. Okay, here's red less than 5. So less than 5 does not mean 5. It means less than 5, which would only include 2, 3, 4. So the red cards that are 2, 3, 4 are hearts and diamonds. So there's 6 of them. Multiply 13 times 6, we get 78. 52 times 52 is 2,704. And we can get a decimal approximation 0.029. Okay, please stop me if you have questions. We have one more part on here. So what we are paying attention to is how many cards we were drawing. So on the first one, we only drew 1 card. And because we were drawing 1 card and we were asking, like in part B, face card or heart, we have this addition that happens. If we draw more than 1 card, we are going to have multiplication. So we have drawing 2 cards, the probability of drawing a first card and drawing a second card. So there's the multiplication. The second thing you have to consider is whether you're replacing or not. This is with replacement, so that denominator stays the same. Part 3, on the same worksheet, randomly draw 3 cards without replacement. So if we're randomly drawing 3 cards without replacement, then we know the denominator is going to change as we take the card out and put it to the side. The denominator for the next draw is going to always change. Part A says, what is the probability of drawing 3 black cards? So out of the 52 cards, there are 26 black cards. So I know I'm going to multiply 3 different times because I have 3 cards I'm drawing. 26 out of 52 is the first. When I draw the first card, put that black card to the side. So now I only have 51 in my deck. And because I drew a black card on the first draw, then now I only have 25 left to choose from. On the third draw, the denominator is now 50 because I have 2 cards sitting out now. And I have a second black card sitting out. So now I only have 24 left in my deck. Multiply across the numerator, you get 15,600. Multiply across the denominator, you get 132,600. And if you get a decimal approximation, it's 0.118. Part B, find the probability of drawing a 4, a red 7, and an ace. Probability of 4, a red 7, and an ace. Without replacement, I have 3 cards. I know it's all multiplication. My denominators are 52, 51, 50. So I know that right away. Probability of drawing a 4. If I go back up to my deck, there are 4 4s. So the probability of drawing a 4 is 4 out of 52. There are only, and then that does not affect the next draw as far as the red cards. So of the red 7s. So if I look at the probability of drawing a 4, there's 4 out of 52. So now I know I have a 4 sitting off to the side, but I still have 2 red 7s in the deck. And I still have 4 aces in the deck. The numerator changed in part A because they were black cards. They were all black cards. So it affected, when I took the black card out, it affected the second draw and the third draw. Part B, each of the cards is not affected by what was drawn, but it definitely was affected because you didn't, the denominator was affected because you didn't replace the card. So if you multiply all that out, 4 times 2 times 4 is 32. And the denominator, when you multiply the denominator across, you get that 132,600, which is approximately 0.00. And if I don't carry it more than 3 places, I would just get zeros. So I'm going to take this one out to 4 decimal places. And then we have the last one, What's the probability of drawing a 3 of a kind? 3 of a kind means they're all the same number or same face card or same ace. So 3 of a kind would be all 3 cards were sevens, or all 3 cards were queens, or all 3 cards were aces. So when I take my first card, and then I have a second card, and I have a third card. Whatever I draw right here, the other 2 have to match it. So I'm going to draw a first card. Say it's a 2 of hearts. Once I draw my 2 of hearts, that is what I have to match. I have to match the 2s. If my first card is a king, I have to match with kings. So the first card is really, it's not really a probability. It's just 1. It's 100% you're going to draw 1 card. So 52 out of 52, you have a probability of drawing 1 card. We don't care what that first card is. We care what happens on the next 2 draws, because whatever that first card is, I have to match what that first card is on my second card. So I'm not replacing, my denominator goes to 51. Okay, so let's say I drew the let's say I drew this 2 of hearts. So I drew a 2 of hearts, it's sitting outside. So now I have to draw on my second draw and my third draw 2s. In order to get a 3 of a kind, I need them to be all 2s. So this 2 of hearts is now outside of my deck. So that means I only have the 2 of clubs, the 2 of spades, and the 2 of diamonds left. So I have 3 left out of the 51. So 3 are left. I took a 2 of hearts out, say, so now I only have 3 2s left. So now let's say I take a 3 of, or sorry, let's say I take a 2 of clubs out. So now what's sitting outside of the deck, I have a 2 of hearts, my second draw is a 2 of clubs. So now I only have 2 left that are 2s. So then I have 2. So it doesn't matter what the first card is, but I have to match the second and the third card to whatever that is. The denominator changes, 51 and 50. And then the number of cards that qualify to match that first card is 3 cards, then 2 cards. So my multiplication across the numerator is 312. No, it's not. Yeah, it's fine. 312. Across the bottom is 132,600, which is approximately 0.002. Okay, let's go on to the next problem, which has to do with the carabiners. So the next page on this worksheet is with the carabiners. Carabiners are metal loops with spring-loaded gates or openings used as connectors. In a box of 11 carabiners, we have 4 that are defective. If I randomly select 2 from the box without replacement, we need to find the following probabilities. Okay, so let's just play with this idea first. In the box, I have 11 carabiners, 7 are defective. That means the remaining 7 are not defective. I have 11 carabiners, 4 of them are defective. That result is 7 are not defective. without replacement. We're selecting 2. So let's go to part A. And it says find the probability that both, let's not go to part A yet. Let's play a little bit more. Let's explore this a little bit more so that we can get a full picture. If I look at just drawing one carabiner, let's let N equal not defective and let D equal defective. So if I take, and I want to know what's the probability of drawing a not defective carabiner out of my box of 11, and what's the probability of drawing a defective out of the box of 11. So not defective, there are 7 of them. Defective, there are 4 of them. So these are just probabilities and other things that I want to consider as I answer the questions. So I wasn't asked to do this, but I need to do this so I can understand how to find the probabilities as we go. Okay, so now let's look at part A. Part A says, find the probability of drawing both defective. So that really is a probability of D and D. So think about the marbles that we just worked on that problem. Probability of drawing a defective part and another defective part. So out of the 11 carabiners, 4 are defective. We are not replacing, so that means there's only 10 left in the box. And because my first draw was defective, there's only 3 defective ones left in the box. So I get 12 out of 110, which is approximately 0.109. Part B, find the probability that both parts are not defective. So we're looking at the probability of NN. Probability the first one's not defective times the probability the second one is not defective. Probability not defective, there are 4 that are not defective. Oh, 7. Oops, sorry, not 4. I'm coming back up here in my box and remembering what I have. I have 4 defective and 7 not defective. Okay, so not 4, but 7. I'm not replacing, so I have 10 in my box. And because I took a not defective carabiner out, there's only 6 of the not defectives left in the box. So 42 out of 110, which is approximately 0.382. Okay, so before we go on to part C, let's build a tree diagram. And my tree diagram on the first, it's only going to have 2 layers because I only am drawing 2 parts. So the first draw is either going to be defective or not defective. The second draw, if I drew a defective one, the second draw is either going to be defective or not defective. If I draw a not defective first, then the second draw will either be defective or not defective. So my sample space will be DD or DN, ND or NN. See that from the tree diagram? We're just reading across. DD, DN, ND, NN. So those are the only options. Those are all the possible ways I can draw two carabiners. Okay, so we found the probability up here, the probability of both being defective, we found it to be here, right? We found the probability that they are both not defective right here. So what is the probability of defective, not defective, or not defective, defective? Probability of DN is the probability of D times the probability of N. Out of the 11 carabiners, there are 4 that are defective. Take one out, there's 10 carabiners, and there are 7 that are not defective. So we get 28 out of 110. Probability of not defective and then a defective. So probability of N times the probability of D. Probability of not defective is 7 out of the 11. Take one carabiner out, so there's 10 in the box and there's 4 that are defective. So we end up with the same probability as we did the other way with the defective, not defective. So I'm looking at my sample space here. Probability both defective. Probability both not defective. Probability that one is defective. Moving on to part C, let's try to apply what, okay, so probability 1 is defective. This is not part C, but I want to expand on this before we jump into part C. Probability that 1 is defective. That means either defective, not defective, or not defective, defective. Right? That means in that case, in that sample, 1 is defective. Either the first one is defective or the second one is defective. So the probability, okay, we just did that up here. The probability of defective, not defective. Write that down. So 4 out of 11 times 7 out of 10, or out of the 11, 7 are not defective, and then 4 out of 10 for the defective. So we get 28 out of 110, or again, 28 out of 110. We get approximately 0.509. So a little more than 50% chance that 1 is going to be defective when I draw it twice. Part C. Part C says, what is the probability that at least one part is defective? Here is a rule you need to memorize. I know I said you don't need to, but this one you do. Probability of at least one is the same as 1 minus the probability of none. This is going to be so helpful for you. Whenever you see at least 1, the probability of at least 1, you want to jump into this because you'll calculate 1 minus the probability of none. So let's see what that means here. The probability of at least one part is defective is the same as 1 minus the probability that none are defective. Probability of at least one defective is 1 minus the probability that none are defective, which is the same as 1 minus, what is the probability of none defective? Isn't that mean NN? First one's not defective, second one is not defective. None are defective. We already calculated that, but in case we want to do it again, probability that none are defective is 7 are not defective. On the second draw, that would be 6 out of 10. Go ahead and multiply it out. 42 out of 110 is the fraction. Approximately, then we get 1 minus 0.382 just by taking the 42 out of 110, which gives us a probability of 0.618. So my sample space that we created, the sample space that we created up here with the tree. So the probability of DD, probability of DD, probability of DN, probability of ND, and probability of NN. Probability that both are not defective is 0.382. Probability of not defective and then defective. 0.25 to 255. This is the same probability. And then the probability of defective, we found right here, 0.109. This is called the probability distribution. So you're taking all of the options of your sample space and you're connecting it to probabilities. So if I look at this and I say that I want to find the probability of at least one defective. So I'm asking you about part C again. At least one defective. We solved it with this rule because it was fast and easy. Probability at least one is defective. Okay, well, it's that case where it's defective first, then not defective. Or it's this case, or both are defective. I can find this answer by adding I can find the answer to the probability that at least one is defective by considering all of the options. The first option is probability that this first one is not defective, but the second one is, or the probability that the first one is defective, the second one is not, or the probability that both are defective. Let me just erase give myself a little more space here. So the probability at least one defective is the probability that you have the second one defective, or the first one defective, or both of them defective. Those are all the ways that at least one is defective. So if I add those up, probability of defective, not defective, so I'm just coming back up here to the table, 0.255, not defective, and then defective, again, 0.255, and the other case is here. So if I add all those together, I get 0.619. And is that not what we got here? We got 0.618. Little round, it's a little bit of a round off error with 0.618. But this rule helps us get to the answer quicker. We don't add up all of these three parts, but rather, instead of adding all these three parts up, we take one minus probability of none. Probability that none are defective, one minus that gives me the same answer. Okay, and I want to be just explain the decimal where I got 9 instead of 8. It's from round off error. So as I'm computing all of these decimals here, I'm rounding off. So I'm rounding off, which creates a round off error. So that's why there's a little discrepancy between the 0.619 and 0.618, is because of that round off error there. But using the rule, hugely helpful. Probability at least one equals one minus probability none, because you only do one calculation, probability of none, and we subtract from one, versus doing 3 separate calculations, adding them all together and getting your answer. Okay, that's all we have time for today, and I went way long. So not way, it was just 10 minutes. So we did not get to the pregnancy problem, which is on this worksheet, but we will do that Thursday, and then we will finish up the probability problems from the worksheet we started with on Thursday as well. I encourage you to keep practicing. Use the Help Me Solve This, use View an Example, but not as a crutch. Go to intuition, try to work these out, struggle. When you're completely stuck, maybe walk away for 10 minutes or so, come back, and then have a fresh perspective, and then use the View an Example or Show Me How to Solve This. Okay, so that's it. Keep working hard, and it will pay off, I promise. Okay, bye.